Okay, so now that the meeting is now being recorded, let's start. And before starting, let's have a recap first for what we have been discussing for the past couple of months now. So last prelims, we have already discussed about the analysis of tension members. So this is a screenshot from our lesson before. So analysis and design of tension members. So in our lesson during that time was about limit states such as cross-sectional area yielding, net area rupture, block shear, stability by slenderness ratio and whatnot. And after we have discussed about the analysis and design of tension members, we have discussed about the analysis and design of compression members. So this was the screenshot from our lesson before. So we have been introduced with the effective length, the slenderness ratio, the elastic critical stress, and the flexural buckling stress. And the last time, so last midterms, you have also discussed about the analysis of flexural members. So confirmation everyone, can you see my laser pointer now?
Yes,
Yes, sir.
Okay, so that this is for the analysis of flexural members. So during this, we have solved for the design moments using this and the lateral torsional buckling, shear, deflection, and various local failures. So in the analysis of the flexural members, we have checked the compactness, we have checked the zones, and using these zones, we have solved for our nominal moments that we would be using for our flexural members. So summary, we have solved for this axial tension, axial compression, and flexure. But what if we would be combining two of these cases right here? So we can't just combine both tension and compression here, because if we would be combining these two, they would just simply cancel out. So let's just leave that alone. Okay, but if we are to combine compression and flexure, is it possible? Or let's say tension and flexure, is it possible? So the short answer to that is yes, it is possible, since that is our lesson for today. So when is the case that both tension, axial tension, and flexure is present in a structural system, a structural member? So it is in this case right here. So in this first case right here, it is a hanger subject to an off-center tensile load. So there is a tensile load here, and it is not concentric. So meaning if it is not concentric, it has an eccentricity. So it is eccentric. So if there is the presence of eccentricity in your tension member, we would be considering moment in it. Why do we consider moment here? It is because aside from this PU right here, we would be having a lever arm of our eccentricity. So if we would be multiplying our PU times eccentricity, so this is to be your force times lever arm, that is equal to moment. So it would be this internal moment right here. So can you follow, guys, that if you have an eccentricity here, you would be having a certain moment, even there is no couples. So confirmation, do you still follow, everyone?
yes, sir.
Okay,
Yes, sir.
about for the others. Mr. Villar, are okay?
Yes, sir.
Okay, so that is for the first case. And as for the second case right here, though our tensile load here is concentric, so meaning by concentric, it is acting on the centroid of your section, we have a transverse load here. And as you can see here, this is actually a uniformly distributed load that is transverse to your section. And if we are to get its resultant, it would be this. So this is to be the resultant of the load on the right. And if you would be having a certain load here, so let's say that that is to be PL, so lateral load, there is also the presence of our lever arm. So let's say that that is to be X. So force times lever arm, that is to be a moment. And with such, we now have a where is my pen? We now have a internal moment right here. So aside from it being subjected to tension, it is now also subjected with moment. So if it is subjected to bending moments, we can now consider this structural member right here as a flexural member. Okay, and as for this third case right here, so this is a beam subject to a uniform gravity load and an axial tensile load. So as you can see here, there is an axial tensile load here and there is a uniform gravity load here. And if that is to be a beam, you should have a support here. So there is a support here. There is also a support here. If we are to cut a section in this beam right here, so let's say that we would be cutting it here and we are to consider one side of the beam. So let's consider left side. So we would be having a certain moment here. So that is to be the resultant of your uniform gravity load and this reaction right here. So we would be experiencing some internal bending considering this beam right here. And aside from the moment that I am showing you right now, let's not forget that there is the presence of our axial tension right here. So these are some of many cases wherein both tension and flexure is present in a certain structural member. So how can we check the adequacy of such? So we can check the adequacy of such by using these equations right here. Confirmation, can you read these equations, everyone? I mean, is it clear? The one I underlined?
Malabo yung subscripts yata, sir. Sa akin,
Oh, okay, sir.
Hindi po.
Isusulat ko na lang mamaya. Actually, pwede ko naman na isulat ngayon, sir. So, I will just be writing it here. So, piece of R over piece of C plus 8 over 9 times M sub Rx over M sub Cx plus M sub R's of Y over M's of C's of Y. And this equation right here should be less than or equal to 1.0. Oops, medyo iurong ko pa onte para makita nyo pa. So there, so it should be less than or equal to 1.0 for us to check, for us to confirm that our section is adequate in both tension and flexure. And if this would help, try kong i-zoom in para makita nyo yung subscripts, no, sa mismong equation. So this is AISC equation H1-1A and AISC equation H1-1B. Is it clear now, guys? Everyone?
Yeah, okay na.
Okay.
Yes, sir.
Okay, sir. Okay, anyway, so PR over PC. So, how can we know on what, by the way, erase ko muna para malinis. Okay, so how can we know on what formula we would be using for our analysis? So we have these limiting factors right here, PR over PC. So we would be comparing the ratio of your PR and PC to 0.2. But first things first, what is PR and what is PC? Our PR is our required axial strength or our tensile strength. And if that is to be the required, so if you are to use LRFD, that is to be your factored load. So may it be 1.2 dead load plus 1.6 live load, or let's say that is to be 1.4 dead load. So whichever is higher in both. And if we are to use ASD, that is just the service load. So DL plus live load. So that is for PR. And actually, for M's of Rx and M's of Ry, that is just the moment. The factored moments if you are to use LRFD, and that is to be the service moments if we are to use ASD. So, same lang siya dito. So, 1.2 DL plus 1.6 DL. So, to put it in this manner, so the ones in the numerators are the required strengths, and the ones in the denominator are your actual member strength. So for your PC, so your PC is equal to PN over omega if you are to use ASD, and if you are to use LRFD, that is to be phi times PN, where our value of omega is equal to 1.67 and our value for phi is equal to 0.9. So that is to be for PC. So same is true as with our MCX. So MCX, that is equal to the nominal moment about the x-axis divided by omega if we are to use ASD. And if we are to use LRFD, that is to be MCX is equal to the nominal moment about the x-axis times phi, which is our reduction factor. So this one right here, this fraction right here is only concerned with the bending about the x-axis, and this fraction right here is only concerned with the bending about the y-axis. And if your member doesn't have a moment about the y-axis, so just cross this out and solve for this. But if your member does not have a moment about the x-axis and it does have a moment about the y-axis, just cross this out and solve for this. And it is as simple as that. So let's just have an example problem here. So for our example problem, a W12 by 40 tension member with no holes is subjected to axial loads of PD 110 kilonewtons, PL is equal to 135 kilonewtons. So this is to be the dead load and this is to be the live load. And as for this, it is also subjected with bending moments of moment along Y, that is to be 14 kilonewton meters, that is to be the dead load, and MLY, or this is to be the moment about the y-axis that is brought about by the live load, so that is to be 35 kilonewton meters. So is the member adequate if our unbraced length LB is less than LP? So our steel is of A992 grade 50 specs. So it has yield stress of 50 KSI, and we are to use ASD in this problem. So once again, if we are to deal with a tension member that has bending moments in it, we would be using these formulas right here. So it is same as these formulas right here. Okay, so we would now be getting its sections, its section properties using our Excel file. So this is to be our Excel file, which is the AISC shapes database. And since we are to get the properties of a W12 by 40, we would now be searching. So W12 by 40, and so this is to be W12 by 40. I would just be highlighting it and scroll to the right up until you find the section properties that you would be needing. And in our problem right here, this is to be the properties that we would be needing. So that is to be the gross sectional area, the plastic section modulus, the moduli. So dalawa sila, no? And if you can remember during our meeting before about flexural members, before you can solve for the nominal moment, you must check first the compactness of your section. But in this case, I have already solved for the compactness of our section for us to save time. So I have concluded that this section right here is indeed compact. And if you don't know how to solve for the compactness of the section, you must watch our video before. So I think 3 weeks ago. So I have uploaded that 3 weeks ago. Okay, so since we are to use these formulas right here, what we are to solve here is the values, are the values of PR. So PR, PC, and do we have a moment about the x-axis here? So wala, we don't have a moment about the x-axis here. What we have here are moments about the y-axis. So M's of R's of Y and M's of C's of Y. So we would be solving for this for us to check if the member is adequate. Okay, but first things first, we must choose whether we would be using this formula right here on the bottom or if we are to use this formula right here on the top. So we would be getting the ratio of PR and PC. Okay, so once again, our PR is equal to the required, the allowable strength of, the allowable tensile strength of our member. And since it is said here that our tension member has no holes in it, and if we are to go back to our lesson before in the analysis of tension members, so we are to consider limit states such as yield, gross sectional yielding, and net area rupture. And since our member has no holes in it, we would only be considering gross sectional yielding because our net area or our AE is also equal to AG, and if we are to multiply it by our rupture strength, which is higher than Fy, we would be having a higher number. So meaning the critical limit state here is that of cross-sectional yielding. So are we clear on that, guys? Confirmation? Now mag-govern dito is yung cross-sectional yielding and hindi ang net area rupture kapag wala tayong holes dito. Confirmation, everyone?
Yes po, sir.
Okay, so thank you. So with that being said, for our cross-sectional yielding, that is to be Ag times Fy. And as for the value of Ag, I have copied this from the AISC shapes database. So that is to be 7550 millimeter squared times Fy, and our Fy is, so hindi ko pa pala na-solve yung Fy, no? And it is said here that we are to use grade 50 specs. I mean A992 grade 50 specs. And if you can see in the calculator to your right, so 50 kips per square inch, so 50, we would be multiplying that by our conversion factor of 6.895 to convert it into megapascals. And our answer here would be 344.75. But for the sake of our classes, I would be rounding them to the nearest whole number. So I would then be using Fy is equal to 345 megapascals. So if that is to be our yield strength, that is to be 345 megapascals. So multiplying this, we would be having an answer of, so looking once again to the calculator to your left, so 7,550 times 345, we would be having an answer of 2604750. By the way, guys, since our PR, since we are to use ASD, I have forgotten the the factor of safety. So this should be divided by our factor of safety, which is omega, and our omega is equal to 1.67. So are we all right there, guys? So nakuha naman kung bakit meron tayong omega dyan?
Yes, sir.
Okay,
Sir.
so that is to be Pn over factor of safety. So considering that, since our omega is to be 1.67, so 1.67. So from that, the value of our PR is now equal to, so 7,550 times 345 divided by 1.67, and our PR right now is 1559730.539 newtons. But if I want to convert it into kilonewtons, I would be dividing 1,000. So convert lang natin. So our PR is now equal to 1,559.73 kilonewtons. Hello, sir.
Clarification.
Yes, sir.
ASD ba yan?
Yes, sir. ASD.
Load reduction. Tama ba? 1.67.
Yes, sir. Because yield limit state, sir.
Yung units.
Yes, sir. Just for the tensile stress, sir? Okay, sir. And so however, if we are to use LRFD here, instead of dividing this by our factor of safety, which is 1.67, we are then to multiply this. So for example, wala ito. We are then to multiply this by our reduction factor phi, which is 0.9. So that is if we are to use LRFD. But in this problem, we are to use ASD. So we are to divide it by our omega, which is 1.67. So that is to be for our PR. So we already have PR here. And as for our PC, oh, by the way, this is not PR. So this should be PC. So PC nga pala to kasi ito yung strength na mismong ating W12 by 40. And for our PR, so I should have solved for this first. So ang PR natin is the required strength, and if we are to use ASD, that is to be the service loads, and service loads, that is to be 110 kilonewtons and 135. So 110 kilonewtons plus 135 kilonewtons. So equals, so 110 plus 135. So 245 kilonewtons. So this is to be our PR. Okay, guys, take note that if we are to use LRFD, so note, if we are to use LRFD, this should be the factored loads, which is 1.2 times 110 plus 1.6 times 135, or 1.4 times 110. So whichever is higher, you would be using that for your LRFD, but we don't need LRFD here yet. Okay, so if we already have the values of our PC and PR, so we would now be solving for the ratio of our PR and PC. So PR divided by PC. So our question here is it greater than or equal to 0.2, or is it less than 0.2? So we don't know yet. So that's why we are solving for it. Okay, so question mark ito. So PR over PC, that is to be 245 kilonewtons divided by our PC of 1559.73. And our answer here would be, so 245 divided by 1559.73. So that is to be 0.157. So is 0.157 greater than or equal to or less than 0.2? So as per inspection, that is less than 0.2. So meaning if our answer here would be less than 0.2, we would be using this formula right here in the bottom. So it would be this, since we have satisfied this equation right here. So okay, we already have our PR, we already have our PC, and as for bending about the x-axis, we don't have that, since there are no moments about the the x-axis. We only have the moment about the y-axis, which is this. And as for m's of r's of y, we would be solving for that using these values right here. And as for the m's of cy, we would be solving that using the analysis of flexure members. So I would just be copying these parameters right here so that we wouldn't be going back to this slide. So lagay lang natin dito. So I would be deleting this. So okay. So once again, we would be using this formula right here. And as for our MRY, so wait, MRY is equal to okay, hindi ko kinopya sa kabilang slide ang ating moments, and our moments right here is, if you can look at the calculator on your left, so that is to be 14 plus 35. So it would be these values right here. So moment about Y, that is the dead load and the live load. So 14 plus 35. So I would just be writing them here. So 14 plus 35, and that is equal to 49. Okay, so 49 kilonewton meter. So we already have PR, PC, we don't need this. And as for MCY, we would be solving for that. And for our MCY, I would be writing them here in the bottom part. So MCs of Y, this is to be equal to nominal moment divided by factor of safety. And once again, if we are to consider flexure, our omega once again should be 1.67. So for our MN, so there is actually an added note here. It is said here that is the member adequate if our unbraced length is less than LP. So if we are to go back to this slide right here, our lesson before, if your LB is less than your LP, it means that you wouldn't be experiencing lateral torsional buckling. So zone 1 siya. And if you are to deal with structural members in zone 1, you wouldn't be experiencing, once again, lateral torsional buckling. That's why your nominal moment is equal to your plastic moment. So going back here again, so that is to be plastic moment divided by omega. And our plastic moment is simply Fy times plastic section modulus. So, okay, equal sign. So, Fy, which is 345. Oh, by the way, I would just write it here first before substituting. So, omega. So, this is to be equal to 345 MPa times, so I have written here Zx, pero malito. It's because that we are actually solving for MCs of y. And if I would be substituting Z's of x here, what I am solving right now is MCx. But once again, we don't need MCx. So this is erroneous. So this should be Z's of y. So I would just be writing it here. And our Z's of y is 275,000 millimeter cube. So from that, we would now be dividing it by our factor of safety of 1.67. So from that, our MCY is equal to, so 345 times 275,000 divided by 1.67. Our answer here would be 568,11377.25 Newton millimeters. And if I want it to if I want to convert it into kilonewton meters, so I would be dividing 1,000 for newtons to be converted into kilonewtons, and I would be dividing another 1,000 for the millimeters to converted into meters. So equal sign, and our answer here would be 56.81 kilonewton meters. Confirmation, everyone, can you still follow?
Yes, sir.
Okay, so 50. Okay, thank you. So 56.81 kilonewton meters. Okay, so we already have everything that we need. So isulat ko lang dito para mailagay ulit natin sa next slide. So MCs of y is equal to 56.81 kilonewton meter. So I would be erasing this solution right here for us to have a space for our interaction formula. So since our PR over PC is less than 0.2, once again, we would be making use of this equation. So PR over 2PC. So I would just be substituting it right away. So our PR is equal to 245. So color coding na lang natin para mas maayos. So 245 kilonewtons divided by 2PC. So divided by 2 PC, and our PC is 1559.73 kilonewtons. So kilonewtons would cancel out. Then we would be adding this by, so plus, since we don't have the value of MRX and MCX, we would be making use of MRY and MCY. And our MRY and MCY are 49 kilonewton meters and 56.81 respectively. So 49 kilonewton meter divided by 56.81 kilonewton meter. So solving for this equation, so this is to be equal to, so 245 divided by 2 times 1559.73 plus 49 divided by 56.81. And our answer here is equal to 0.941. So 0.941. So is it less than or equal to 1.0? So the answer here is yes. So meaning our section is adequate. So can you still follow, everyone?
Yes, sir.
Are there any questions? So mukhang wala naman. Okay, so if you don't have any more questions, let's proceed with the next problem.